Welcome to this lecture in quantum field theory. So now what we will do is quantize the Klein-Gordon field as harmonic oscillators. So we have already discussed the motivation behind studying quantum field theory, and we introduced the Klein-Gordon Lagrangian. So what do we want to do now? So we wish to quantize now the Klein-Gordon field. And how will we do that? Well, what we will do is start with a classical field theory description, which we will then quantize by taking our dynamical variables and promoting them to operators that will obey certain canonical commutation relations. All right, and once we have that, what we will do is solve the theory to find the eigenvalues and eigenstates using the harmonic oscillators as an analogy. And throughout the video, I will actually study the harmonic oscillator case just so that we can be reminded of the procedure before we actually go into the quantum field theory version. So let's begin with just a quick reminder of classical field theory. So a reminder, and this is not even classical field theory at this point, this is just a little bit of classical mechanics. So what we want to know here is that we are going to be, at least in the case for a single particle, what we had was a Lagrangian that depended on the position of the particle. This is for a single particle, and also its first time derivative, okay, or its velocity. And once we had that, we could also find the conjugate momenta that was associated with that dynamical variable. And we did that by taking the partial derivative of the Lagrangian with respect to x dot. Okay, so that's how we found the canonical momentum in classical mechanics. And with this, we could then find the Hamiltonian description. And this is why we're going to be interested, because we want to then be able to find the Hamiltonian once we're dealing with quantum field theory. So the Hamiltonian we found by taking the canonical momentum, multiplying it by x dot, and then we subtracted the Lagrangian. So that's what we did before. Another thing that you may have encountered in classical mechanics is the Poisson brackets. So the Poisson brackets of x and x, for example, was 0, which is the same as the Poisson brackets of p and p, and also the Poisson bracket of x and p was simply 1. Now, we could also use Poisson brackets to determine the equations of motion. So, for example, the Poisson bracket of x and the Hamiltonian, this gave x dot, and also the Poisson bracket of p and the Hamiltonian, this gave us p dot. Okay, so that's what we had in the case of just classical field theory. So now we will take some aspects of this and now generalize it to go to the quantum field case. So let's now go to, so let's slowly begin going to quantum field theory. So now we will not be dealing with a Lagrangian per se, right? Not just the Lagrangian, but rather the Lagrangian density, right? Because now we have fields. So this thing here was simply classical mechanics single particle, and now we're going to go into fields. So for now, we're just going to fields. It's not quantum yet. So this was single particle, and now we're going into fields. So now we will see fields, okay? So in fields, now we will have a Lagrangian density, right? Which now, in our case, will depend on our field and also on its first derivative. Now, we discussed this briefly in the previous video, in case you watched that, so that may be helpful. And in analogy to the canonical momentum that we had, right? What we had just right up there, we can define now pi, which is going to be basically p, but now in the case for fields, which is going to be the partial derivative of the Lagrangian density with respect to now the time derivative of the field. Okay, so that is the equivalent of the canonical momentum that we saw for the single particle. And with this, we can now build the Hamiltonian density, which I will write using this cursive h. Now it looks a bit weird, but that's just cursive h, I promise. And this is going to be, in analogy to before, simply the canonical momentum times, now instead of x prime, it's going to be phi prime, not prime, dot. and then minus the Lagrangian density. Okay, so that's how we write the Hamiltonian density. And then the Hamiltonian, this is going to be, well, simply the integral over all of space of the Hamiltonian density, right? So integral over all of space of pi phi dot minus the Lagrangian density. Now, in analogy to what we saw right here, so with the Poisson brackets, these ones, we are also going to define now canonical relations. So these ones are going to be as follows. So in the case for, we are still in classical field theory, right? So we haven't really gone quantum yet, keep that in mind. So for classical field theory, we want now that our fields, if we have phi of x and phi of, let's say, y, right, some other variable, we want to take this to be at the same time, so x0 equal to y0. This has to be 0, right? This is the equivalent to x and x, for example. And this also has to be, of course, the same as pi of x and pi of y. And now we are going to have the equivalent of this one right here. So if we have phi of x and pi of y, here, of course, at the same time, all of this is equal time. So all of this is always at equal time. So x0, y0. This, now it has to be 1 if our coordinates are the same, but it has to be 0 if they are different. So that means simply this is going to be at delta x minus y. And of course, we are in 3 dimensions, so this is going to be delta 3. So this basically means x1 has to be equal to y1, x2 to y2, and x3 to y3. So with this in mind, right, this is what we're going to be using. Of course, this is still classical field theory. Now we will just begin going into the quantum version, and we will do that by looking at, right, we're going to go step by step. We are going to now look at the Klein-Gordon Lagrangian density. So what happens when we take what we just saw and apply it to the Klein-Gordon Lagrangian density? And what is that? Well, we derived it in the previous video. So if you don't know where this comes from, go back and watch that. So this is 1/2 d mu phi minus m squared phi squared over 2. Okay, so if this is the Lagrangian density, then we need to find a few things. So first we need to find the canonical momentum pi. So the conjugate, momentum here, this is, let's see, the derivative of the Lagrangian with respect to phi dot. Okay, so maybe let's rewrite this because we don't have any phi dots here. Keep in mind d mu, this is simply the time derivative, comma, spatial time derivatives. So what we have here is going to be 1/2 of phi dot squared, and then minus, they have del phi. Okay, so we simply expanded the d mu's, right? This is simply time derivative, comma, spatial derivative, and then time derivative, comma, spatial derivative with the relative minus sign. And then we have minus m squared phi squared over 2. Okay, so that means if we take now the derivative with respect to, phi dot, well, only this part depends on phi dot. So that simply means this is going to be phi dot. Okay, so that is what the canonical momentum pi is. So with this, we can now work on building the Hamiltonian density first. So let's begin with the Hamiltonian density. So this would be pi dot phi dot, but well, that's also pi, so we actually have this pi squared, so the momentum squared, minus, now comes the Lagrangian density, so that's 1/2. Now instead of phi dot, let's also write pi, and then minus minus, so we get plus del phi, and this is 1/2. Actually, I completely forgot about the 1/2. Is it? Yeah, it is 1/2. So sorry about that. I completely forgot about that. And then we have, plus m squared phi squared over 2, and this also has over 2. Okay, so that is the Hamiltonian density. So now the Hamiltonian is going to be, well, the space integral of that. Now, of course, we can put these two together. So we have pi squared over 2 plus the phi, now the phi here over 2 plus m squared phi squared over 2. Now that we have this classical field theory description, it's time to quantize. So now we quantize, right? So now we quantize. And how do we do that? Well, as we said, what we want to do is now promote our dynamical field variables into operators. So what we'll do now is say, well, what do we know about operators in quantum mechanics? Well, we care about now their commutators. So basically our Poisson brackets will now turn into commutators. So what we'll do now is take the relation that we had up there. So now we have not the Poisson bracket, but rather the commutator of our fields, still equal time. So these are now the equal time commutation relations, which is going to be 0 still. And same thing for our momenta, x0 equal y0. And now the other relation here is between our field and the momentum. Now think of this as the analogy of x and p. So when we were young, right, in kindergarten, we learned that x comma p was I h bar, right? That's what we learned in kindergarten. But now we are not in kindergarten anymore. So now we are a grown up, right? So now what we have is not x, but rather the field phi that depends on x, and not p, but rather pi, that here very well could depend on some other variable y. We have to keep this in a very, very general way. This is, of course, equal time commutation relation. So we have to just specify x0 and y0, which are the time components, right? Here, x and y are 4 vectors. So their 0th component are the time components. This has to be I h bar, except that we are using natural units. So h bar is equal to 1. And this is, of course, in the case where our x and y vectors are going to be the same. So this has to be delta 3 x minus y. So these are now our commutation relations. And now we have gone into the quantum world. So now we have officially quantized the field. So now we are in quantum field theory. All right. So now what we will do is start studying the solutions, right? We said now that we quantized, we want to solve the theory. We want to now find this Hamiltonian, right? What is pi, right? What is the explicit form of pi? What is phi, right? So we want to find the Hamiltonian. We want to find pi and phi. So let's begin. Well, how could we do this? Well, we can think back to when we solved the Klein-Gordon equation for a single particle and say, okay, so we know that that is a solution, so we could build a solution on top of that, right? We can take basically the Fourier transform of the solution that we have and just work on the Fourier space. Now, there's quite a few ways to think about it. You can also note, of course, and that's where we're going to be slowly going towards. I will go to that conclusion in a moment, but in case you already noticed, what we have right here is almost the Hamiltonian of harmonic oscillators. Now, you may not have noticed, it's okay, but this is basically p squared over 2 in the case where we are not dealing with mass, but just densities. And this is basically the m squared omega phi squared. It's kind of like that. I'm just going for an analogy here, right? And this thing right here, that is simply, well, that is a bit complicated because we are actually not really diagonalized yet in the space. So that's why we're going to go into the Fourier space. So that's another reason why we want to go into the Fourier space right now. So let's just do that. Now, we will write the solution, so the field phi of x. We can write this as the Fourier transform. So we can write this as 1 over 2 pi. Now, this is a very important point. There are several normalizations that you could use. Peskin and Schroeder uses 2 pi cubed, but another book, for example, Ashok Das, uses 3 over 2. Now, it doesn't matter which normalization you use. The main difference is that when you go all the way to the end and find the commutation relations that you care about, there's going to be a difference in normalization. In fact, there's going to be a difference right there. Okay, I'm going to be using 2 pi to the 3 over half because that's what I like. But again, it really doesn't make a difference. There's a lot of different normalizations. So if you see a difference, it's because of that. But know that as long as you also know what the commutation relations are, then you are good to go. Okay, so now we're going to be integrating over all of space. So d4k, and now e to the minus ikx, and phi with this wobbly thing, k. All right, so that's going to be the solutions that we are going to be working with. So the first thing that we will do is plug this back into the Klein-Gordon equation, right? So the Klein-Gordon equation was simply this, right? This times phi of x equal to 0. So let's now plug these solutions in so that we can just learn a few things about it. So if we plug it in, right, we have to take the derivatives. We can actually put all of this inside the integral. So 2 pi 3 over 2. Then we have the integral d4k, so d4k. And this is, now we can separate these derivatives as d squared dt squared minus here nabla squared plus m squared, all of this phi k. Oh, I forgot about the e to the minus ikx phi here with that wobbly thing equal to 0. Okay, now here the space derivative is very simple. We simply derive this twice. We get a minus sign from the I squared and a k squared, which is simply going to be here the momentum, since we are just deriving the spatial parts. So this will be plus p squared. Okay, and now notice that if this is supposed to be 0, then we need that this times this has to be 0, right? Because it's simply going to be the Fourier transform of 0. So we need p squared plus m squared, this thing, to be equal to 0. Now, what is this? Well, this may seem quite familiar, and if not, don't worry. We will write it in a more suggestive way. So this thing right here, we can write as an angular frequency squared, and then just multiply through. So we have phi, so the phi double dot plus omega squared phi k. Now what is this? This thing right here is simply the equation of a simple harmonic oscillator that we have seen many times. So we can see that the equation of motion that this now satisfies is actually that of harmonic oscillators. And that's why we were talking about that the fields itself are just going to be basically a infinite amount of harmonic oscillators, each one oscillating, right? And when one of them is excited, then you have a particle. So that's what we're going to be going into. But that's also why it's very important that we understand a little bit about how harmonic oscillators work, just a quick reminder. And also, I will do the same procedure that we will do later with quantum field theory, but just with the study of harmonic oscillators, so that we can see the procedure before and then we go into it. Now, keep in mind that the Hamiltonian of a simple harmonic oscillator was h here is equal to 1 over 2m p squared, right? Plus 1/2 m omega squared, now let's call it omega p to keep the same notation, x squared. And what we learned in quantum mechanics is that we can write p and x in terms of ladder operators, which were very convenient. So p was I times the square root of m omega over 2. I'm of course copying this from my notes because I don't know this by memory. And then we have square roots here, 1 over 2m omega times a plus a dagger. Okay, so that is what we had. Now from this, back in quantum mechanics, and for example, we had x comma p, right? And this was equal to I h bar, but of course, h bar is simply 1. So let's just go ahead and check this so that we can refresh ourselves a little bit on how we work with these kind of equations. So let's just plug in x and p. We can pull the constants out. Actually, maybe let's just go step by step so that nobody is confused here. So here we have commutator of I square root m omega over 2, a minus a dagger, comma, square root of 1 to m omega, a plus a dagger. So now we can take all of our constants. So we can take I and then square root of m omega over 2 times the square root of 1 over 2m omega. And then we have the commutator of a minus a dagger, comma, a plus a dagger. Okay. And let's see, so here we can cancel a few things out. So m omega, they cancel out, and we have just 1/2. So we have I over 2. So we have I over 2, and this has to be equal to I. So of course we can just divide by I, and we just get this is equal to 2. So this is equal to 2. Now there's a few ways we can go about solving this commutator. You can multiply, just solve it explicitly. You can also use properties of commutators, whatever you want. In this case, we could just keep in mind that the commutator here, we can separate it as the following. So we can say commutator of a comma a, right? So that's the commutator of these two, plus the commutator of a comma a dagger, which is the commutator of these two. And then we have plus, or rather minus, so the commutator of these two, so that's a dagger comma a. And then we have minus the commutator of a dagger, and this would be comma a dagger. Now this of course is 0, right? A minus a, well, that's the same. And here as well, a dagger minus a dagger, that's also 0. So this commutator is 0, this commutator is 0. And then keep in mind that you can switch the order of a commutator by just putting a minus sign in there. So we can just switch these. So we have a dagger, and this minus turns into a plus. So we simply have that 2 times a comma a dagger is equal to 2. So that means a dagger is equal to 1. See? There we go. So that is what we find from just using this, checking this commutator. And this is, of course, something that we all also knew to be true. And well, I guess we also saw that a comma a is 0, which is the same as a dagger comma a dagger. So that's a few new things that we learned, or rather remembered from doing this. Now the next thing that we will do is go back into our Hamiltonian and now plug in our respective values for p and x. So that is the next part of our plan. So we will just plug in the values for p and x. So maybe let's do it so that we can actually see them. So maybe I'll just also keep them, just move them down here. Okay, so let's just plug in p and x into the Hamiltonian so that we can write it in terms of the ladder operators. Now, all that we are doing now, we will also do later in the quantum field theory part. So that's why it's good to pay attention here. Now this is 1 over 2m. Now p squared, we get a minus 1, so minus, then m omega over 2, and then this part squared. So, actually, I'm missing a dagger there. It didn't come along with the copy here. So we have a minus a dagger squared. Okay, then we have plus 1/2. So plus 1/2 m omega. I guess I should be using the same omega. So this here is also omega p. Omega p squared, and now x squared. And this is also p, by the way. I've just been a bit lazy with my notation. And this would be 1 over 2m omega p, a plus a dagger squared. Okay. And now we can cancel this m with this m, this omega with this, and here we can cancel m and m. Okay. And then we also have 1 over 4 and omega that we can factor out. So we can factor out omega over 4. All right. And then we have minus. Now let's just multiply through here. So we have a squared minus a dagger minus a dagger a. Keep in mind, they don't commute, so be very careful. Plus a dagger squared. And then we have plus, now this thing, which is a squared. Yeah, I was just seeing that this parenthesis is much larger than this. It confused me. Plus a dagger plus a dagger a plus a dagger squared. Now, because of the minus sign, we have that this and this cancel out, this and this cancel out, and then we have this is equal to omega p over 4, and now we have plus a dagger a. So we get 2 times a dagger plus 2 times a dagger a. All right. And now this is simply going to be omega over 2. And now we will just do a little bit of a trick. So we will say a dagger, because we now want to build a commutator, because we know what the commutator is between a and a dagger. It is 1. So if we can build it, we can simplify this a little bit. So we have a dagger. Now we want minus a dagger a. Okay? And then we have plus a dagger a plus a dagger a. So this thing here is 0, right? We just added 0. And this one here, well, it comes from there. Okay? And the 2's, keep in mind, they just canceled out with that 4 over there. So we haven't done anything illegal. We just added a 0. And with this, we can now write it with a commutator. So we can write this as the commutator of a and a dagger, and then plus 2 times a dagger a. And we know what this commutator is. It is simply 1. So from here, we write this as omega, and we can just multiply inwards with this 1/2. So we get a dagger a plus 1/2. Okay, so that's how you can write the Hamiltonian for the harmonic oscillator in terms of the ladder operators. You may have already seen this. But what's important also to note is that you have a lot of harmonic oscillators. What you're going to have is basically a sum of this, right? If you have a lot of different harmonic oscillators, you're going to have a sum over this. Now, once we have this, we can now define the ground state. Okay, so we define a ground state, which is of course the one that if you act on it, you get 0, right? So the ground state is that if you use the lowering operator a, you get 0. That's the whole point. So with this, we can now study the harmonic oscillator once again. So if we have the harmonic oscillator acting on the ground state, for example, we can see what is the energy of this ground state. And well, we just, actually, let me get rid of the sum because we're not using the sum. So this would simply be omega a dagger a plus 1/2. And this is all that is acting on the ground state. But a acting on the ground state is 0. So that's going to be 0. So we simply get omega over 2 acting on the ground state. So this is the eigenvalue, right? So that means that that's going to be the energy of the ground state, which is something that we already knew, right? And now from this, we can also build the rest of the spectrum. Now, why are we doing this again? Because we are going to do this later in the quantum case, and it's important that you know what this looks like. Actually, this is quantum as well. I meant quantum field case. But it's important that you know what this looks like, okay? Or at least be reminded. All right. So now, what is the energy of the first excited state, right? Using the ladder operator once. Well, for that, it's very useful to know the commutator between H and a dagger. Why? You will see it in a moment. So maybe let's go to the side. So we wonder here, what is the commutator between the Hamiltonian and the raising operator, right? So the commutator between the Hamiltonian and the raising operator, well, this is simply Hamiltonian times a dagger minus a dagger times Hamiltonian. But what is the Hamiltonian? The Hamiltonian is that. So plugging it in, we get omega p, which are going to be able to factor out from this entire thing. And then we have a dagger a times a dagger plus 1/2 times a dagger. So a dagger over 2. And then we have this part. So that's going to be minus a dagger times the Hamiltonian. So we get a dagger a, and then minus a dagger over 2. Okay, so the a daggers, they're simply going to cancel out. So this and this, they cancel out. And then we can factor out the a dagger in the front. So we can have this as omega p, a dagger, factor of a dagger minus So A dagger minus A dagger A. And that's simply the commutator of A and A dagger, which we know is 1. So this is simply omega P A dagger. Okay, so that is the commutator of the Hamiltonian with A dagger. Now, why do we care about this? Because of the following. So if we want to have the Hamiltonian acting on the first excited state, which will give us the energy of the first excited state, well, we don't really know what it is just now, but we do know some other things. So we would really like to switch around the Hamiltonian with the raising operator, because we do know what H acting on 0 is. So that's why we're doing this. So we're going to switch around the order of the Hamiltonian and the raising operator. So that means, let's go here and see, okay, so this is what we know. So from here, we can see that, maybe let's write it up here, H A dagger is simply the commutator H comma A dagger plus A dagger H. So we will rewrite it. So this thing right here is simply going to be the commutator H comma A dagger plus this other one, but let's just multiply through, so acting on the ground state, plus A dagger Hamiltonian acting on the ground state. Okay, now we know what the commutator is. The commutator is simply omega P times A dagger, and this is acting on the ground state, plus A dagger times the Hamiltonian acting on the ground state. But what is that? We also know that already. That is simply omega P over 2 times the ground state. So we can factor out some things here. So we have omega P 1 plus 1/2 acting on the first excited state. Right? So here we can see then that the Hamiltonian acting on the first excited state there is simply this thing right here. Now this is of course a very familiar form, because if we do this over and over and over and over again, right, we get that the nth state is simply going to be A dagger to the n times the ground state, and its energy, right, if we do this again, this 1 will turn into a 2, then a 3, then a 4. So that means that just the energy of the nth excited state is simply going to be omega P n plus 1/2, which is of course what we have known for a very long time, right, since kindergarten, when we first encountered the quantum harmonic oscillator. Okay, but in analogy to this, we are very soon going to be doing a bit more complicated things. All right, so now what we want to do is simply go back to our expression that we started out with, right, the Fourier expansion of our solutions. And now we are going to just do the same procedure, right, that we just did, but this time in the quantum field theory version. Okay, so let's move all this to the side quickly. And now we'll repeat the same thing. So first of all, we want to learn a little bit more about the solution before we actually get started. This will be very quick. And it's actually kind of the same procedure because we don't know much about this phi hat here, right? We don't really know much about it. So what we will do is the following. We will put this into the Klein-Gordon equation once again, right? d mu plus m squared is going to act on this. So we have 1 over 2 pi to the 3/2. Again, this is simply a convention. There are other possible normalizations. In Peskin Schroeder, they use 2 pi to the 3rd, and you will see the difference in the end. E to the minus I kx and phi. Okay, so now if we let it act on this, what we get is 1 over 2 pi 3/2. And now what we will do is just let this act just as d mu, so that what we end up with, so we have d for k, is going to be now k squared, right? So we are going to end up with the 4 vector k. And then we have actually going to be minus the 4 vector k plus m squared, and then, you know, everything else, e to the minus I kx and that. So if we want this to be equal to 0, because of course the Klein-Gordon equation is equal to 0, then what we need is either our Fourier nodes are 0, which is not really what we want, that would be kind of trivial, or m squared is equal to the 4 vector k squared. Okay, now the 4 vector k, keep in mind, this is k0 squared minus the just 3 vector k squared. Okay, so that means that k0 squared is equal to m squared plus the k vector squared, or k0 is equal to either plus or minus m squared plus k squared. Of course, this isn't particularly new, right? This is going to be what we call plus or minus the energy. And there is something that I do want to mention here, because this condition that we have here means that we will only be able to work on solutions for the Klein-Gordon field when that condition applies, which is what we call on shell. So this is what we say on shell, which basically means that we are in the case where m squared is equal to k squared, right? Because there are a bunch of possible combinations of momentum, but we want only these combinations. Now, for now, it doesn't have much meaning. It's like, okay, just a word. But in the future, we will continue to work on that and go even further. Since we know that either this phi is 0 or this condition is satisfied, then we can write phi of k as a delta of k squared minus m squared, or the other way around. I mean, it doesn't matter. It's the same, times just some function of k, okay, which is going to be here these a's, which will very soon we will relate to the raising and lowering operators. Okay, so that condition has to be satisfied. So now we're going to be working a little bit further with the Dirac function here, with the Dirac delta or distribution. Don't get upset at me if you're a mathematician. So what we can do is rewrite k squared as k0. Maybe let's put the line there, otherwise it doesn't look like a k, so let's just do it like this. So k0 squared minus k squared, the vector here, and then minus m squared. So we can factor out the minus, we get k squared plus m squared, but k squared plus m squared is simply the energy squared. So this thing here is simply the energy squared. So this is ek squared. So this is basically a condition on the energy. And now we can use a very important property of the Dirac delta, which is that this thing right here, when we have this function inside of the Dirac delta, we can write it as 1 over 2 the absolute value of k0, and then we can separate the delta into delta of k0 minus ek plus delta of k0 plus ek. So that's simply a property of the Dirac delta. Okay, so with that in mind, one last thing we can do, of course, is note that the absolute value of k0 is simply ek, right? K0 is either plus or minus, but the absolute value is simply ek. So we can get rid of this and just write it as ek. Okay, just a quick reminder, in some other books, different notations may be used. For example, I know that in Peskin Schroeder, they used here instead of ek, omega p, I believe, right? And so we may make that connection again at some point. All right, so plugging this into our phi's, right? We plug all of this back in here. And so maybe let's go to the side a little bit. So actually, I think if I paste, I should still have that. Yes. So let's go to the side and just plug this in. So we have, well, 1 over 2 pi normalization constant, d for k, e to the minus I kx. And now we have that whole thing. So we have 1 over, so maybe let's write it here. So we have 1 over, so that's 2 ek. And then we have delta of e minus, or rather, so it's not e minus, it's k0 minus e, sorry. It's k0 minus ek. And then we have plus delta of k0 plus ek. And of course, each one, or actually all of this, is now multiplied. So if we go back, all of that is multiplied by ak. So ak, which we don't really know what it is just yet. So here we can just multiply through, right? So we can multiply through. We have 2 pi 3/2 integral d4k. Now let's multiply through by all of this. So maybe let's put this in here, so 2ek, and then we have first e to the minus ikx. So let's separate this first. So let's write this as like this. So we can write this as e to the minus ik0 x0 plus I k vector dot x vector. Okay, so we just separated it. Why? Because that way we can apply the condition of the Dirac delta. Okay, so if we do that, now we have applying the Dirac delta. That means, right, k0 has to be equal to ek. In that case, first of all, notice that we will no longer have a d4. We are no longer going to be integrating over 4 dimensions, because now the time dimension is limited to a single value, right? The k0 has to be ek. So no longer will this be d4, it's simply d3 now. Now, as of the rest, we can now apply the Dirac delta in the meaning that k0 will now be either ek or minus ek. So in the first one, we have e to the minus I ek x0 plus I kx. And then we have a of k, but k here is the 4 vector, so we can write it as k0 comma k vector, and k0 is ek. And then we have the second one here, which would be e to the, now it is minus ek, so we have I ek x0. I don't like the way my e looks, so maybe let's redo it quickly. So ek x0, and then we have plus I kx, and all of this multiplied by a, and now we have minus ek comma k. Okay. So did I forget to write anything? I don't think so. So now what we can do is just note that these two expressions are kind of similar, but here we have a to the minus ek. There's kind of a sign difference. So what we can do is take this part and just change k to minus k, because we are integrating over the entirety of the values of k anyways, so that doesn't really affect in any way, and that way our notation will be a lot cleaner. So we're simply going to go, k vector will go to minus k vector, right? So we add a minus sign here and a minus sign here, a minus there. Okay, so now that we do that, we can do something very nice. So here we can just rewrite this as a of the k4 vector, and this here now will be a of minus k4 vector. So this will be minus k4 vector, okay? And we can now basically just go back on our notation, just go back here in the exponent. We know that ek is simply k0, so we can just go back to k0 and go back to k0. Whoops, I deleted the x0 as well, so k0, x0. And now just write this again as just the dot product of the k4 vector and x4 vector. So by doing that, we note here that we have a minus sign that is factoring out. So we have minus I kx, right? That way when we expand, we get I k0 x0 minus I kx with the vectors, and with the minus sign we get what we had before. And here we don't need a minus sign, this is simply I kx. So like that. Okay, so now we found a relatively simple expression for our phi. So for our phi of x. But now keep in mind that our field is real, right? So what we said when we started out is that the Hermitian conjugate of our field has to be the same as our field. So that's what we said. So let's see what that condition tells us about ak and a minus k. So by taking this, we have phi dagger of x, which is, well, of course, it doesn't affect the constants at all. I will put them inside, so d3k. And then we have 2 pi 3/2 2ek. And then the exponent here will be e to the I kx, a dagger of k plus e to the minus I kx, and then a dagger of minus k. And these two expressions have to be equal, right? So these two things have to be equal. So that means, well, everything outside, everything there is equal already, so there's no problem. Now inside the negative exponent, they both have to be the same. So that means that from comparing those two expressions, a dagger of minus k has to be the same as a of, let's see, a dagger of minus k has to be the same as a of k. And then from the other one, right, comparing these two, we get that a dagger of k has to be equal to a of minus k. So by plugging this back in, we can now find a much nicer expression. So we can now find that phi of x, this is going to be the integral d3k over 2 pi 3/2. Again, you may get a different number there if you're following a different book. 2ek, this ek you can sometimes see written as omega p, just so that you know that. And that's not a nice k. And then we have e to the minus ikx a of k plus e to the ikx, and now a dagger of k. And now you can see that we have written our phi in terms of the ladder operators, even though we haven't really checked that they are ladder operators yet. But in analogy to the quantum harmonic, the quantum harmonic oscillator, this is a pretty nice step. Now what we want to do is note the following. We saw that k0 is simply the, well, either plus or minus the square root of m squared plus k squared, like the k vector. But since we are on shell, right, there are two possible values, either plus or minus, and we are going to be sticking to the minus to the plus for now. So that means that this expression is positive. And that also means that k0 actually depends on the k vector. So in reality, a of k and a dagger of k only depend on the k vector, not on the time part, right? Because that one also depends on it. So for that reason, it is customary that we define a of k over the square root of 2k0. So this is simply convention, right? So this, we are just using a convention so that we end up with the same notation as other books. And this is going to be now a of k vector, right? So now we are going to write that this depends only on k vector. And the same thing applies for the dagger version. So the 4 vector divided by the square root of 2k0 is going to be the a dagger of k vector. So this means, of course, that a of k4 vector is going to be the square root of 2k0, but k0 is ek, times a of k3 vector. And similarly, we can find here that a dagger of k4 vector is going to be the square root of 2k0, which is of course ek, so ek, a dagger of k3 vector. Okay, and now we can plug that back into our expression up here, right? So by the way, this is 1 over in case it isn't very clear. So now we can just plug it in. So maybe let's do it maybe right underneath. I just get rid of this part. So let's do it here. So now we have phi of x. This is going to be integral d3k 2 pi 3/2 1 over 2ek. And now each one of these is going to give us a factor of square root of 2ek. So that means we now have to multiply this by the square root of 2ek. So that means that when they simplify, we end up with the square root down here. Okay? So then we have e to the minus ikx, a of k vector, plus e to the ikx, a dagger k vector. Okay, so that is going to be the expression that we use for the fields. So now what we want to do is simply to find the other things that we need for the Hamiltonian. Keep in mind, our objective is precisely to build the Hamiltonian in terms of ladder operators so that we can see that indeed the quantum field theory considers the entire field to be filled with harmonic oscillators. But for that, we still need to find pi squared, or just pi, which will of course give us pi squared later. So for that, we need to keep in mind, well, how do we find pi? Well, that's precisely why we did a little bit of a recap on just Lagrangian Hamiltonian mechanics, which tells us that pi is simply phi dot, right? Pi of x is simply phi dot of x. So we just take the time derivative here. Now the time derivative, keep in mind, we can expand this as minus I k0 x0 plus I kx as vectors, and then e to the I kx here. We can just write this, let's see, as this would be plus I k0 x0 minus I kx. So if you take the time derivative, you get I k0 from both of them, but you will get a relative minus sign here, right? So we get integral d3k 2 pi to the 3 halves, and then we get k0, but k0 is the same as ek. So ek square root of 2ek, and we also have an I, so I. And then we have minus e to the minus I kx, a of k vector plus e to the I kx, a dagger of k vector. Okay, and now something we will do is just take out a minus sign so that we end up with this minus that. Okay, so basically just change where the minus is. Okay, and that is pi. Of course, we can just simplify this a little bit further here by simplifying the ek, so that we end up with the square root of ek divided by 2. Okay, now that is our pi and phi. So we have all the tools that we need. However, at this point, I will change notations slightly because I think it's likely that many of you are following Peskin Schroeder's book. And if that is the case, then you will have encountered slightly different expressions. So in Peskin Schroeder's, they don't really show you the derivation, but the only differences are the following. So they have a different normalization. So in Peskin Schroeder's, they use 2 pi cubed instead of 2 pi 3 over 2. There. So that. And another difference is that they call ek omega p, right? Making the connection to the harmonic oscillator like we did at the beginning of the video. So ek is now omega p. And instead of k, they have p's, right? They are talking about just momentum a bit more directly. So they just write it as such. So I'm just going to make sure that the notations match. And you can see how you can go from this to that. Now, instead of writing a and parentheses k, they write it in subscript. But instead of k, they use p. Okay, so that's another difference. So this is a sub p. And then the same thing goes here. Now, we could have just stick to our old notation, but I think that this is a bit more useful in the future. It's a bit more comfortable. And it's also going to help you in case you're following that book. And another difference now is just that they had defined the exponents to be negative in the other way around. So basically this is positive for them, and they consider this to be just the 3 vectors, and that's actually why the signs changed. Because again, if you don't consider this, then you end up with a plus sign, right? So they basically got rid of the time components, and they just were left with the rest, right? So if you do it like that, you end up with a minus sign here. And similarly down here, you get plus and minus. And of course, they are dealing with 3 vectors. This is now px. So this is px, and this is also px. So px. And similarly here, this is px, and this is px. Okay, so now that we made notation match that of Peskin Schroeder's, we can now continue because we have found pi and phi, and now we can do a few things. So, well, the first thing we could do is just go straight for the Hamiltonian, but I think there is some value in taking just a quick moment and making notation a bit cleaner. So we are again going to follow Peskin Schroeder's notation. And what they do now is that they take the dagger portion and just change p to minus p for both of these expressions. So p to minus p. So p to minus p. And by doing that, we will get that e to the minus ipx will be e to the ipx, but now we are dealing with minus p. So this is basically the same logic as before, okay? But the main difference is that, I mean, the reason why we can do this is because we're integrating over every single value of p, so just switching the order here will not make any difference. And in principle, we would have also omega of minus p, but omega, since the energy is quadratic in p, it doesn't matter. You get the same result, so we don't have to worry about that. Okay, so we change that, and we also change this. So that and minus p. And the whole purpose of doing that is that now we can factor out the exponent. So we can now write e to the ipx out there, and you can see now the expression is just a little bit simpler. So same here, we can just factor it out. So e to the ipx. Okay, and now something we can do, I mean, first of all, let's note that we had some commutation relations before for our ladder operator. So in the case for the quantum harmonic oscillators, we saw that these commutators, A dagger, these were 0. And of course, that is still going to be the case now. The only difference will come from the commutator between A. Now, of course, all of these would have to be P prime and things like that. If we have the commutator between AP and AP prime dagger, we are just allowing the possibility of there being two different momenta. This is going to be, and now this is where the normalization comes from. If you used, right, so if you had 2 pi to the 3/2, then this is simply the Dirac delta cubed of P minus P prime. But if you used, so if you used 2 pi cubed, then this thing is going to be 2 pi cubed times the Dirac delta cube P minus P prime. So this is 1 if P and P prime are the same, and 0 if they are not the same. Okay, so that's the new commutation relations that we have for the ladder operators, which is just an extension of what we had before. It's literally the same, but now we have to consider that P is in 3 dimensions, right? You need it to be the same in every dimension. Okay, so that was just a quick comment. And now let's check, for example, another thing that we did. So we said previously that phi of x, right, the commutator between phi of x and pi, now I think we said y. What notation did we use previously? Let me check. So previously we said y. Okay, so let's stick to that. So basically I want to check this, right? I told you this, we were going to assume that, and now we're going to check that. Or basically see also what that implies. So we have phi of x, comma, and instead of x prime, so I guess we're just going to use y, even though, again, it's just notation, doesn't matter. And this, of course, is equal time commutation relations. So now we just plug everything in. So this would be, let's see. So we have phi, which is going to be integral of d3p over 2 pi cubed 1 over square root of 2 omega p, and then we have AP plus A of minus P dagger, E of IPX, and then we have comma minus I, so just writing the minus outside, square root of, or rather integral d3p over 2 pi cubed, then we have the square root of omega p over 2, and then we have AP minus A of minus P dagger. And we have to consider this is now different momenta. So this is P prime, omega P prime, P prime, P prime. Okay. And then we have E to the I P prime Y. Okay. So that's the commutator that we now want to solve. So we can just take all the weird things out of the integral. So we can, out of the commutator. So we can take the integrals, the constants, everything outside. So we have minus I, then we have integral d3p, d3p prime divided by 2 pi to the 6th. And then we have square root of omega p prime divided by 4 times omega p. And I think that's okay. And then we have e to the I p x plus I p prime y. Okay, so that's the way to write it. Okay, great. So now we have only the commutator left. So then we have AP plus A minus P dagger and comma, and then we have AP prime minus A minus P prime dagger. Maybe let's use these parentheses so that we don't get confused with the commutator. So like this and like that. Okay, so now let me copy this because I don't want to write it down again. So Control C, Control V. Okay, and now let's just expand this commutator using properties of the commutator. So we can write this as the commutator of AP, comma, AP prime, and then AP prime. Then we have minus the commutator of AP, comma, A minus P prime dagger. And then we have plus the commutator of A of minus P dagger, comma, A of P prime. And then we have one more commutator, which is minus the commutator of A minus P dagger, comma, minus A minus P prime dagger. All right, and there we go. So now, well, let's go back to the relations that we know. We know that the commutators between A and A are 0, and A dagger and A dagger, they are 0. So this is 0, that's easy. This is 0, that's easy. So no worries there at all. Now, the issue that might exist comes from this. Not really an issue, but at least that's a bit more difficult. So what we just saw is that AP, comma, AP prime dagger, this is, in our normalization, 2 pi cubed del cubed of P minus P prime. Okay, but we don't really have this formula. What we have is AP, comma, A of minus P prime dagger, right? That is that case. So this would be 2 pi cubed del cubed of P minus P prime. Okay, so we just get P plus P prime. That's the difference. And then we have the other commutator. So the other commutator, A minus P dagger, comma, A P prime. This is minus, we are just changing the order of the commutator. So A P prime, comma, A minus P dagger. And now we use the formula above because it's the same thing. So this would be, well, with the P prime switched. So this would be minus 2 pi cubed del cubed of P prime minus P. So P prime plus P, right? So nothing too crazy. So that means that these two expressions are basically the same because this one right here is 2 pi cubed del cubed of P prime plus P, or P plus P prime, it's the same. And the other one is minus this same thing. So we end up with minus 2 times that thing. All right? Now we can simplify a few things. So of course, 2 pi cubed is going to cancel out with 2 pi to the 6th. So we get here 2 pi cubed. Then we have this 2, which will cancel out with this 4 inside the square root. This minus will cancel out with a minus in front of the I, so we get just I. And then we have the delta. So that means P prime has to be equal to P. Okay, so that is the next important part. So let me just get rid of this to make some space. So that means P prime is simply equal to minus P. So let's now plug it in. So that means I D3P. Oh, I missed the D3 there. And of course, that also limits the values of P prime, because if we are supposed to be summing over every single value in the integral, then we are only left with 1. So the Dirac delta is killing that integral. So that means 2 pi cubed Now, again, this is gone, d3p prime is gone, because we killed the integral with the Dirac delta, right? It's only non-zero at one particular value of p prime, so if you're summing over every value of p prime, it's zero everywhere except when p prime is minus p. Then we have the square root of omega of minus p divided by omega p, and then e to the I px minus I py, and that's it. So here what we have, keep in mind that omega p is quadratic in p, right? Omega p, this is p squared plus m squared. So of course, whether it is p or minus p, it doesn't matter. So it's the same as omega minus p. So these two things are the same. They're both just omega p or omega of minus p. So you can just simplify them. Okay. And now what we have here, this thing that we have here is by definition, right? By definition, the Dirac delta of x minus y is written as the integral d3p 2 pi cubed of e to the I p x minus y. So by definition, that's what it is. So you can just write this entire thing here as the Dirac delta cubed of x minus y, which is of course the commutator of phi of x and pi of y. All right, so that's what we had seen before. That's what I had told you, but now we proved it, and we also gained some experience in doing algebra with these sort of quantum field theory expressions. Now what we would like to do is actually do what we came here to do, right? So actually find the Hamiltonian. So we said the Hamiltonian is d3x of integral, and actually let's see our expression because I already forgot. So it is right here. So it's d3x, no second integral, p squared over 2. All right. So what we want to find now is the following. So we want now no integral, but rather parentheses pi squared over 2 plus nabla phi over 2 plus m phi squared over 2. So that is what we now want to do. Or was it m squared? I'm just going to double check because I don't want to make a dumb mistake at this point in the video. It was m squared. I'm glad I checked. Okay, so m squared. So with that, well, let's just plug everything in, right? So pi squared, let's perhaps take our expressions and put them somewhere closer. So I'm going to grab these things like that. So Control C and just go back down and just write them here to the side. So that just goes there. Okay, so this would be, I'm going to now write in blue the integral, maybe put a separating line. And now let's begin plugging things in. So pi squared, let's take a look at this. So if we square this, we have a few things. So the minus cancels out, but the I squared gives us another minus. So we get minus, and then we have integral of d3p 2 pi cubed, and then we have omega p over 2, so square root of omega p over 2. Now we're not simplifying it just yet because the second part will have a different p. So this is ap minus a minus p dagger e to the I px, and now we have to multiply it again, but this time we will allow for the possibility of p being different. So that means we now multiply by integral of d3p prime over 2 pi cubed, and then we have omega p prime over 2, and then we have ap prime minus a of minus p prime dagger, and then e to the I p prime x. Okay, so that is just p squared, and this of course has to be divided by 2. So all of this times 1/2, so minus 1/2, right from there. Now for the phi derivative, so we have to take the derivative and square it. So if we take the derivative with respect to x here, we just get p, right? So we get ip. That's all we get. So that means, maybe let's just write it down first. Just nabla phi of x. This is going to be integral d3p over 2 pi cubed, and then 1 over 2 omega p. And then we have, well, it's the same thing here, plus a minus p dagger e to the I px. But now we have to multiply by I pi. So just put an I pi somewhere over here, perhaps. So I p, sorry, not pi. Okay, so now let's just copy this and put it twice. And once will, of course, be with primes. So Control V. And Control V again. Okay, so this would mean this is prime, 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 and plus. And then we have, and 1/2, of course, 1/2. And then plus 1/2 m squared of phi squared. So that just means phi squared, which is what we have right here. So this thing right here squared. So that goes in here, right there, and again. So one more time there, but now we write prime, 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 prime. My handwriting got significantly smaller there, but okay. So now we can do a few things, of course. We can put, well, first of all, square root of 2, square root of 2. We can cancel those, that's simply 2, and we can write it here as 1/4. So just 1/4. We can also put all the integrals together. So we can write d3p, d3p prime, and also 2 pi to the 6th here. So we can just get rid of this. We can also then combine the exponents as e to the I, so e to the I p plus p prime x. That way we get rid of this. We can also combine the omegas, but I don't have much time space, so I'll do it a bit later. And then here in the next part, we can do something similar. So in this part, we can also put, let's see, first let's begin with this. So I and I gives us a minus sign, and let's put the p's together. So we get minus p dot p prime. Then we have 2 pi to the 6th here. So that comes from this. We then put the d3p prime. Let's see. Then we have this 2 inside the square root. Can I somehow hit only the 2? Yes. Which again will give us 1/4 outside. And then we can combine the exponents again. So that would be just like before, just like above. E to the I p plus p prime x. And finally, down here, we can do something similar. So we can put d3p, d3p prime. The 2's will again cancel out, giving us 1/4. So that and that, it gives us 1/4. Then we have 2 pi to the 6th again, so that is now to the 6th. So 2 pi to the 6th, and combine the exponents. So e to the I p plus p prime x. Whew, okay. Phew, so we're making some progress. And now we can just factor a lot of this out. So let's change colors again. So now we can factor it out. So we have the Hamiltonian. This is going to be integral of d3x, integral of, so what is it that we have in common? We have 1/4. So perhaps let's put that first. So let's put our constants first. So this would be 1/4, because all of them have it. And well, that's it. So integral of d3p, d3p prime, 2 pi over 6. So that is common to all of them, right? It's 1/4, 1/4 that thing, and 1/4 that thing. Now the exponents we can also factor out, so e to the I p plus p prime x. And now we have some things that are unique to all of them. So now let's just open parentheses. So here we have minus square root of omega p prime. And then we have the product of, maybe let's just this parentheses, ap minus a minus p dagger, ap prime minus a of minus p prime dagger. Now the second line, let's see, it's going to give us the following. We get, so that's outside, we have minus p dot p prime divided by the square root of omega p prime. And now we have this multiplication between AP and A minus P dagger, but now with positive sign. So plus A minus P prime dagger. And now the third part here with the mass, this would be plus m squared, but now everything else is exactly the same as we just had, so we can just factor it in here, so m squared. That makes things a lot simpler for us and a lot nicer. Okay, so now notice that what we have in this part is the following, right? We can take d3x e to the I p plus p prime x over 2 pi cubed. And what is this? That is simply the definition of the Dirac delta of p plus p prime. So we can now just get rid of that, and some of the 2 pi cubed, and instead write in the Dirac delta. So that would be del cubed of p plus p prime. Now, what is the effect of the Dirac delta? Well, the Dirac delta, what it does is it kills the integral of d3p prime, because now we can't sum over every single value of p prime. We can only take the value where p prime is minus p. So let's now plug in that value. So every p prime we will now replace by minus p. So this is minus p, and this here is minus p, so maybe in blue as well, so minus p, and this minus p prime, that's now going to be plus p, right, minus minus. Then we have here minus p prime, so that's going to be plus p, so we get p squared. Then we have here omega minus p, and finally here we have a of minus p, and here we have a of plus p. So we get rid of the prime and just plus p. Okay, now notice, just like before, that omega p is exactly the same as omega of minus p, because they are defined as p squared plus m squared in a square root. So that means that omega p and omega minus p are the same, so this is omega squared. So omega squared in the square root is simply going to be omega, so this is omega p. And the same thing happens here, so that is simply omega p. And now p squared plus m squared is omega squared, right? We can see it right there. So this thing is simply omega p squared. So we can now get rid of that and finally factor out the omega here to the front. So we have omega p. Okay, so that is a lot of progress. And now what we need to do is just multiply through. So we have that the Hamiltonian is 1/4 d3p 2 pi cubed omega p. And now we have, so let's see. Now let's just multiply through. So we have minus ap, a of minus p. Then we have plus ap, ap dagger. Then we have minus minus, so also plus. Actually, wait, what's the second one? Yes, that was plus. Okay, never mind. Then we have a minus minus, so we get plus a of minus p dagger, a of minus p. Then we have minus minus minus, so minus a of minus p dagger, a of p dagger. And now we go into this part. So we have plus ap, a of minus p, plus a of minus p dagger, actually I like to multiply it like this. So let's do a p dagger, then plus a of minus p dagger, a of minus p, and plus a of minus p dagger, a of p dagger. So here we can see that a few things cancel out. So minus ap, a minus p, and then we have plus ap, a minus p. So those two, they cancel out. We also have minus a minus p dagger, ap dagger, and plus the same thing. So that also cancels out. And then these two things are double, right? One's here, one's there, one's there. So we can just write both of them as just 2 times that. So 2 times and this times 2. So those two, we can actually just take them out and simplify it with the 1/4. So that's 1/2. Okay, so now we are in a much, much simpler position, but what can we now do to continue? So now we will do once again our beautiful trick. Here we'll say, well, let p go to minus p. We're integrating over all of p. So again, reversing it doesn't make any difference. And since they are being summed, it's 2 different integrals, so changing one doesn't affect the other. So by doing that, we get 1/2 integral d3p 2 pi cubed omega p. Now notice that in principle, one of these would be omega of minus p, but we know that it's the same, right? Keep in mind, omega p is the same as omega of minus p, which is why we can still factor this out. And then we have ap dagger, plus ap dagger, ap. So now this is kind of a result, but let's go back to what we had previously in the case for the harmonic oscillator. Let me see where it was. In the case of the harmonic oscillator, we found the following, right? So right here, we wrote this as a dagger a plus something, right? And now let's do something similar. So we had, again, take a look at this. We had a dagger plus a dagger a, which is very similar to what we have now. So we will use the same trick that we did back then. We will build the commutator and we will then, continue from there. So let's see, down here. So we will do the exact same procedure as we did in the quantum harmonic oscillator. So here we will just add and subtract something so that we can build our commutator. So since we want to build the commutator of AP and AP dagger, of which we know the result, we still need to have AP dagger AP, and we will also add it so that we are not doing anything illegal. Okay, so by doing this, we have 1/2 integral d3p 2 pi cubed omega p. All right, and here then we have, let's see, so that's AP dagger minus AP dagger. So that is the commutator of AP, comma, AP dagger. And then we still have 2 times AP dagger AP. So here we can multiply through by 1/2. So we can multiply through by 1/2. This is halves and this loses the 2. And now keep in mind, well, what is this commutator? So the commutator of AP, comma AP dagger, we know is simply 2 pi cubed del cubed, and this would be now P minus P. Well, because they are not prime, so that means simply del cubed 0. Okay, so we can now plug it in. So this thing right here would be 2 pi cubed del cubed 0 over 2. Okay, and this is our result. Now keep in mind, right, keep in mind what we have here. So this is basically the ground state energy, right? So this is the ground state energy. This is like that 1/2 that we had in the quantum harmonic oscillator. And this is kind of like that just h bar omega that we had, right? That's kind of just to make the comparison. But now we are summing over every single possible value for P, right? We are summing over an infinite amount of harmonic oscillators, and each one has this number, which is infinite. So that is very problematic because this thing right here is not only infinite, but we are summing it an infinite amount of times. So that is very infinite. So that's infinite. So what that means is that the ground state of our field is infinite, okay? And then on top of that, well, we're going to have the energy of our states. And this is not really a problem in practice because we can only measure in experiments changes in the energy. So if the base energy is infinite, it's not really an issue, even though conceptually it is very problematic. And in fact, we will soon get to that. In the very next video, we will talk about the vacuum energy and why this is so problematic, and just give a little hint as to what renormalization will be later on when we actually deal with this problem and solve it. So with this, we have now found the Hamiltonian and done quite a bit of work. But before we go into actually finding the eigenvalues and eigenstates, we will take a moment to talk about the meaning of the vacuum state energy, which we will do in the next video. So I hope that this video was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.